Yep. So sorry, Ryan, I don't know you, but I know Travis is one of our most neighborly hackers in the community, and always interested to see what he's talking about. If it's going to be radios or watches with radios or Studebakers. I see we've already
probably Studebakers today.
We've ticked off the Studebaker box real quick.
We got Studebakers, we got cats.
More Studebakers and more cats.
Yeah, we got one cat picture that includes a Studebaker.
Excellent. Every combination. Let's see how many we can hit. All right, it's 5 o'clock. You might as well go ahead and take it away. I don't see any reason to wait.
All righty. So the lecture that we'll be sharing with you today is based on a paper that Ryan and I wrote a few years back. The concept is that many of you have done a little bit of reverse engineering and you would like to do more reverse engineering of things. And the skills that it takes to reverse engineer an embedded system really aren't that different from the skills that are necessary to reverse engineer like a desktop application or a game. So today we're going to discuss the fancy tricks that take what might be seen as a hardware problem and converting that hardware problem into a software problem that is then easy to solve on a desktop with modern tooling and a nice environment. Sound good to everybody? So I keep forgetting that there's no audience feedback in this. So Ryan is going to sort of play the part of the audience and interrupt me if I skip over something or fail to express it properly. This is
we'll also be watching the questions, so yeah, feel free to send in those.
All right, so reverse engineering embedded systems is like loads of fun on its own, but at the end of the day, you're just looking at numbers and figuring out what the code does. So what you really want is a worthy project at the end of it that proves that your time wasn't wasted. One of the first of these that was pretty cool is an open source project called Rockbox. I believe this debuted in 2002. The idea was that they wrote their own MP3 player application and then reverse engineered commercial MP3 player hardware in order to port this application to run on it. So you can run this on an iPod, you can run this on pretty much any of the popular MP3 player hardware from 15 years ago, back when people collected MP3s. Another nifty result of reverse engineering is a project that I started back when I lived in New York, or the Godless North, as we call it in Knoxville. This project is called MD380 Tools. It's reverse engineered, it's patches against a commercial push-to-talk two-way radio that can be applied against the manufacturer firmware. So the patches are written in C. They then change the behavior of the commercial firmware that the hardware was designed for, allowing you to add such things as like a phone book of amateur radio operators that are registered for the protocol. You can enable promiscuous mode. You can also dump out the memory and dump raw packets off of the air in order to reverse engineer the settings of a commercial network. And more recently, Tremel Hudson has been playing around with this thing, which is a CPAP machine that he's attempting to firmware patch into being a respirator. In all of these, you need to begin by understanding the architecture that you're working with. Then you need to dump a firmware image, load the firmware image into a reverse engineering tool, and then read it and annotate it until you can understand what it does. So we're going to begin by taking the architecture at a high level, and then we're going to jump into some details. It's impossible to learn how to reverse engineer a new architecture in just 1 hour. So what you should be trying to remember from this are the nifty tricks that make the reverse engineering easier, or the things that might block you and how to get beyond them. And if you remember some high-level details about the architecture and its quirks, that would be good too. Ryan, do you want to take this one and begin like the high level of what an embedded ARM chip is?
Sure. Yeah, so an embedded ARM chip, there's a few examples that you see here. A common one, the STM32, is a small microcontroller. The NRF51 is from Nordic. It's has an RF core in it. And there's many other examples. And in ARM, keep in mind that you have typically 32-bit registers, but your instructions could be 32-bit or it could be 16-bit if you're in thumb mode. And I think that one of the most notable things here to keep in mind as you're reverse engineering ARM is figuring out which context you're in and figuring out how to follow as we jump between contexts. And we'll cover that later. We're not talking about chips that have support for legacy classic ARM instructions. These chips are notably small in size. And when we mean small, and we look at their memory maps, you'll see it's less than a meg of flash, less than 128 kilobytes of ROM, very small RAM as well. So this helps keep the code size that we have to look at smaller, but also means that the developers are going to be playing tricks for code optimization.
And the code can run from SRAM, but it usually runs in place from flash memory. You'll only find it running from SRAM when it's a temporary patch, or when it needs to load a small driver to rewrite flash memory, and for that reason can't be executing from flash memory at the same time. The registers are different than an x86 or AMD64 in that someone put some thought into what the hell they should be and decided to give them meaningful names instead of conglomerates of all the backward compatibility history of the platform of the 1970s. R15 is what you think of as the instruction pointer in an x86. We call it a program counter or a PC in RISC chips, but it's the same thing. R14 is the link register. 13 is the stack pointer, and then your local variables fit between R4 and R12. And it's the child's responsibility to restore these before returning to the parent. While registers 0 to 3 hold parameters and return values, and anytime you call another function, the child can clobber those and not fix them on the return. The program counter is always on when you're in thumb2 mode. And if it were ever even, that would mean that you were executing in the classic ARM mode with 32-bit wide instructions. In thumb2 mode, your instructions can be either 16 or 32 bits wide. And you have very little memory, so the high bits of your program counter are pretty much always consistent and the same and point to flash memory. They can point to SRAM, but in almost any code that you look at, they'll be running consistently from inside of flash. Now, I said that there were two instruction sets. So you've got ARM and you have thumb2. ARM is optional in the smaller chips, but anything that's a little bit older or a little bit larger, older as in like Game Boy or Game Boy Color, Game Boy Advance. I'm actually not entirely sure about the Game Boy first generation. The Game Boy Advance can definitely run both instruction sets. And again, it's the least significant bit of the program counter that tells you which instruction set you're executing. So on the machines that can do both, if you jump to an odd address, you get the thumb2 interpretation of the function that begins 1 byte before the pointer that you're going to. If it's an even address, you don't use the thumb2 instruction set, you use the ARM instruction set. And they did this so that you could freely jump back and forth between these different instruction sets within one single program produced by a single compiler without breaking compatibility and function pointers. R14 is the link register. You can think about this as the return pointer on the call stack in x86, except that in ARM and in Thumb and PowerPC and many other RISC instruction sets, instead of the parent pushing the return pointer onto the stack as it calls the child, it's the child's responsibility to save the link register before calling a grandchild. So if you have a leaf function that you call, a leaf function is a function that has no children of its own, then you branch to that function and it can do its work and return without ever writing to the stack, as long as it doesn't need to save registers or call another child or anything. And because this value gets thrown right back into the program counter, on Thumb 2, it will also always be odd. R13 is the stack pointer. It is always even. It is always 32-bit aligned. And just like in x86, your stack grows down. The differences in the stack behavior are generally in that the stack is sort of manually managed. When you do a call that doesn't directly change the stack, it's the child's responsibility to save things after it arrives. Now, the local variables are also the responsibility of the child to restore. So when you have a Thumb2 function, you'll see it begin by pushing the link register and some of the local variables onto the call stack. And then at the end, it pops them back off. And if you read through the function, you'll see that those are the same registers that it changes by overriding. The requirement is that the state be restored. As long as it goes back to what it was, the child can do whatever the hell it wants with them. Registers 0 to 3 are used for the parameters and the return values. R0 is the first one by the calling convention, and it also contains the 32-bit word that you might return. If you return a 64-bit word, then you will also use R1, and you're under no responsibility to preserve the other parameters. So the child function can clobber any of these that it wants to, and if the parent expects it to be the same, it's its responsibility to save it onto the call stack before branching to the child. But you didn't come here for a description of the number of registers, their names and stuff. You wanted to know how you could get code and begin working with it. So there are a couple of different ways to get the firmware. The easiest, of course, is a firmware update. Ryan, when you're trying to mess with something, what fraction of the time do you get the firmware for free just by looking at an update or executable or the vendor's executable?
I'd say you get lucky on that about 80% of the time. It's
80% of the time,
you can
just hand it off to you. Sometimes it's encrypted.
I mean, not hand it off, but yeah, get it out of like a application download that goes through the smartphone, and you can sniff on the wire or something, right?
Yeah. For Bluetooth,
you don't have to do chip extraction.
For Bluetooth devices in particular, Android has excellent support for logging Bluetooth to disk, which you can then replay in Wireshark in order to capture the firmware update as it goes over the air. Another way of grabbing it is through JTAG, which is a debugging protocol that's very often unlocked. And if JTAG is unlocked, then you can connect a debugger and dump an image out. There's also a ROM bootloader, which can be either locked or unlocked. If it's unlocked, you just read it out through the serial port. But if JTAG or the ROM bootloader are locked, there are still options. So for a specific example, the STM32F0 family is rather popular. It has a vulnerability in its JTAG implementation, which I believe was first documented at Usenix Woot in 2017. The vulnerability is that when you attach JTAG to the STM32F0, flash memory is disconnected from the CPU core and the memory bus. The idea here is that if you think that there's a functionality problem with your device, you're free to connect a debugger to check for that, but you're not allowed to read the code out of it that you would need to copy the device or to reverse engineer it. There's a minor problem here, which is that SRAM is still exposed because it's not disconnected. But the major problem that was presented at Usenix Woot is that when you attach JTAG, Flash is disconnected one cycle too late. So your JTAG debugger can dump out a single word per connection. And by repeatedly reconnecting and resetting the device, the JTAG debugger can dump out all the firmware. The NRF51 is another popular embedded ARM chip with radio support. This is one of the first Bluetooth chips that supported Bluetooth Low Energy and was nice to program. There's a similar situation here in that JTAG was supposed to be able to connect to the chip without being able to dump out all of code when the device is locked. The vulnerability here is that you're still allowed to single step the CPU, and you're still allowed to view its registers. You can read them and you can write them. You're just not allowed to do the fetch from memory yourself. So what they did was, what Chris Brush did in 2015 was he found an instruction that loads the word in memory at the address that's in register 0. It takes that word and it loads it into register 1. And after he finds that instruction, he can then loop through this instruction while changing the value of register 0 in order to dump all of the firmware out the JTAG port, even though the chip is locked. And once you have the firmware, you can unlock the chip or replace it with a new chip, write in the firmware, and continue debugging with full privileges. There are also bugs in mass ROM bootloaders. I used to love writing exploits for these because when you find a vulnerability in a mass ROM and you exploit it, you generally have an exploit.
It lives forever.
Entire chip family. And Ryan, how long do they live?
They never go away. These are the best ones.
Have you ever seen one patched?
I think somebody patched one once by ripping everything out of the field and pushing out all new chips, but it's just not something people like to do.
So the cost of patching this is that you need to begin manufacturing new chips of every affected item in the family, which requires a mask revision. So you're looking at about a minimum of $250,000 per unique model number in the family. So in the case of STM32, they would need to do this separately for the STM32 F407 and 417 and 207 and 217 and so on. So these bugs live a very, very long time. They're the sort of thing where when you find one as a defender, there's not much that you can do about it. You certainly can't upgrade anything in the field. And if you have the decision to burn your warehouses to the ground and remanufacture the chips from scratch over a security bug, you generally choose not to do it. When I'm hunting for a bootloader vulnerability, this is one of my favorite tricks that would never work on a PC. On a PC, you have something called a guard page at address 0. And the purpose of the guard page is that if you ever have a null pointer, meaning that the pointer is 0, and you try to read from address 0, the guard page will trap and inform the operating system, and the operating system will kill your process. And the reason for that is that very often you forget to initialize something, or you try to allocate a buffer when you're out of memory, or any number of things, and you're stuck. On embedded systems, it works differently. This code here, the print data function that I've thrown together that just prints the bytes at a location in hexadecimal, this will dump the beginning of your firmware image if you call it for some length and for address equals 0 on many embedded ARM chips, because quite a few of them will locate whatever memory you booted from to address 0. Meaning that when you dereference a null pointer, you get the beginning of your code. So if you can ever find a place, either in the application or in the bootloader, where you can trick it into sending you data from the device's own memory at address 0, you have a firmware dump. This brings us to the concept of what is in memory at which location. This is the memory map from the Paco GTFO article that Ryan and I published. It was illustrated by Ange Albertini. And you know, the only advantage of doing this lecture remotely is that you can read some of the items on this list. You see that memory is sort of arranged into 512 megabyte regions, and that you've got a full 32-bit address space. So 4 gigabytes of memory that can possibly be addressed for a microcontroller with 1 megabyte of flash and 192 kilobytes of RAM. Here's
and Travis, maybe just to cover it for people how, if they don't have a POC or GTFO article to reference the memory map, how they might find that in documentation or.
Oh, yes. So this is always in either the datasheet or the programmer's guide, which is sometimes called a family guide. It will be unique to your chip, or at least to the chip's family. And it will tell you which pointer goes to which location. If you're so unlucky that you do not have documentation for this, or it's not in the data sheets, you'll find it in the linking scripts. And if you don't have the linking scripts freely available from the manufacturer, you can very often find them included with commercial C compilers. And since you're not trying to use the compiler, you're just trying to read its header files, it's very often not restricted by the compiler's license enforcement. When you look into the list, you'll see that everything is sort of organized by the most significant bits of the address. In this table here, we're only looking at the most significant byte. If that byte is C0, we know that we're looking at mask ROM. This is the ROM bootloader that is physically baked into the chip that cannot be patched or changed. If the first byte is 40, we know that this is in the I/O region, and that the thing being pointed to is something like a counter or a timer or a serial port that it interfaces with the outside world from the CPU core. If the first byte is 20 in hexadecimal, we know that it's SRAM, and if it's 10 in hexadecimal, we know that it's tightly coupled RAM, which on this particular chip happens to be slightly faster, but is not executable. And the vast majority of the pointers that you see when taking the firmware apart will begin with 08, which means that they're in flash memory, which can't be freely written simply by writing to an address, like the other memories can. But it is directly executable, and it's where the majority of our code runs. And then on this chip, the STM32F4 series, if the first byte is a 0, that's aliased to whichever memory we booted from, which is probably either the mask ROM or flash, but the hardware does allow booting from SRAM for development purposes. So let's take a look at some pointers. 20 again, from our list above. 20 is in SRAM. So the first pointer is to SRAM. This is like a global variable, perhaps. The second and the third pointers, those are both odd, and they both begin with 08. 08 tells me that they are in flash memory. But they're being odd, the least significant bit being off by 1, tells me that these are either very strange pointers to a byte offset, which exists but are rather rare, or far more likely, they're odd because they're code and they're thumb 2 code. Because remember, this chip cannot run the classic 32-bit wide ARM instruction set. It's unable to have code at even addresses. So every function pointer that you find will be odd. And then this last one, 4002-3C00, that's in the IO region, which we know because it begins with 40 in hexadecimal. And there are header files for this chip that define all of the IO addresses. This happens to be the flash control register. So whatever function contains this pointer, that function is interacting with flash memory. It might be writing it, or it might be locking the chip. We can then search for these numbers in order to find all of the functions that involve flash memory, or all of the functions that involve a particular serial port. And by doing that, we can then narrow down the code to the individual function that we care about. Ryan, I've been hogging the mic. Would you care to talk about the interrupt vector table and what it means?
Sure, I can go through that. Let's see. Actually, Travis, why don't you start and I'll jump in on the next one.
That'll work. So the interrupt vector table begins at the very beginning of an ARM firmware image. When you get a firmware image, you don't get a .exe file or an ELF file like you would in Windows or in Linux. Instead, you very often get just a blob of bytes. And you need to figure out where those bytes need to be loaded. And you also need to figure out inside of memory where the basic functions are. This table begins with the initial stack pointer, which is a really cool thing, kind of unique to microcontrollers, because it means that from the very instant the program begins running, it has a functioning call stack.
Yeah, so that's R13.
Yes, and that means that your reset vector, which is the entry point for your code, your reset vector can be written in C, and you don't need any custom assembly language to write the beginning of your kernel on an ARM Cortex M firmware image. So these are the beginning bytes of a real firmware image for a Cortex M3 chip. You see that at address 0, we have these 4 bytes in hexadecimal. We have 30, 14, 00, 20. And because this is a little endian architecture, we read them backward. So the first 32-bit word in memory is 2000 1430. The 20 is in SRAM, and that's our stack pointer. And the value after that, reading the next 4 bytes backward, if you follow along, is 08004121. Well, the 08, the most significant byte, tells us that it's in flash memory. And 21, the least significant byte, is odd, which tells us that it's thumb code. So when we decode these, we get first the initial stack pointer, which tells us which piece of RAM the firmware is using. And then we get a bunch of interrupt handler addresses, beginning with the entry point of the program and continuing on to other events, like receiving a byte on a serial port or having the NMI pin or non-maskable interrupt tapped. And we can
Using an
line
RF
it up
chip or
with
component.
pieces of the firmware in order to confirm that we have it loaded to the right location. So the next step, the one that you've been waiting for, is actually loading this into IDA Pro or Binary Ninja or GHIDRA or Vidara 2 and doing something with it. When you
So we'll
try
go
to
through this in the concept. Go ahead, Travis.
Oh, sorry.
Sorry.
When you open the file in IDA, it sees this as a bunch of bytes, and it doesn't really know the instruction set or the loading location or any of those details. So you need to help it out a little bit. The first thing that you need to do is change the processor type manually to ARM little endian. ARM at some point did make big endian machines, and even machines that can switch back and forth between big endian and little endian mode. But these days, it'll be rather rare for you to find big endian firmware. So you choose little endian, and then in processor options, you have all of these fancy variants of the instruction set. But ARM is pretty good about keeping them backward compatible. So about the only thing that you need to do for these images is mark that the architecture does not support 32-bit wide instructions. And then IDA is going to ask you for the memory organization. And if you remember that memory map that I showed you earlier, this is where you present the memory map to IDA. So we do need a RAM section, or code that tries to read and write RAM won't properly decompile. And we also won't be able to track the global variables very well. And we definitely need a ROM section. But IDA defaults both of these to being at address 0, and the RAM to not even being of any size. So we correct it by two methods. The first, the easy one, is the RAM. We know from the datasheet where RAM begins and how large it is. Here I begin RAM at the address with a high byte of 20, because that's what I found in the memory map of the datasheet. And I set the size to 128 kilobytes, because that's also the value that I find in the datasheet. The ROM I load to a strange address. It's 0800 and then C1000. And the reason why I do that is because in this particular device, there are two kernels. And the first sits at the very beginning of flash memory and acts as a sort of recovery bootloader to start the second one. And the offset for the second one, I had to find by reading that first bootloader's code. So now that I know that it begins just 48 kilobytes further in memory than the documentation says, I can apply that in IDA and have everything loaded at the correct location. And there's one more thing that you'll need to do, or IDA will give you total garbage-free results, which is that when IDA loads an ARM image, it's a little bit confused about the instruction set. Because on the ARM architecture, you have two different instruction sets and you can freely jump between them. So you need to use alt+g and set the t value to be 1. When you do this, you then told it that you want a code 16 section instead of a code 32 section. And from that point on, the disassembly will be correct. And then you can begin exploring and marking up your functions. At the very beginning, it knows nothing about it. So you see code 32 as your organization. Everything is at the correct loading address, and the bytes are correct. But IDA doesn't know where any functions begin. So the first thing that you do is you type alt+g and set t equals 1 in the dialog to change code 32 to code 16. The next thing that you do is you use the D key to mark these data bytes as being data words. So once we mark all of them up as 32-bit words, we find the interrupt table, and it's very large. It's more than a page in this architecture. And each of these 32-bit addresses after the first one is a valid interrupt handler that the CPU will jump to when the write event happens. We can then use this for a sanity check. If we made a mistake at this point, or up to this point, if our alignment is off, if our configuration is wrong, there are tells that can let us know that we're about to waste our time by reverse engineering gobbledygook, and let us sort of step back a minute and take a second look. The first thing to check is that some of the instructions are only 2 bytes wide, implying that we're properly in thumb mode. The other thing to check is that any function which is a parent, meaning that it calls another function, should begin by pushing at least the link register and maybe some other registers. And also at the end of that function, it should pop those back off of the stack and into the registers that they came from before returning. We should also check that every target of a branch and link instruction, which is how function calls work, that every function call is to a reasonable address, meaning that when you look at the address that it's targeting, you find the entry point of another valid function. This one isn't as useful as you would expect it to be, because the branch and link instruction is relative in thumb2, meaning that if I've loaded my image to the wrong address, function calls will still work and will still jump to the correct address because they inherit the same mistake as our loading. And then at the end of the function, after the program counter is restored and the function goes back to its parent, we will either find another function, or Thumb has something called a constant pool. And the constant pool is used instead of where x86 would use immediate values. So in x86, you could have an instruction that contains a 32-bit word inside of it. In Thumb2, the longest instruction is only 32 bits, so there's no room for that constant to fit. So instead, you point relatively to the end of your function, where you have a list of all the 32-bit values you might want to load, and it can be fetched from there. This is an example of a Thumb2 instruction. It's a short one. I used this one during a sanity check. The purpose of this function is just to make sure that everything is loaded right. We see that at the very beginning, it pushes register 4 and the link register to the call stack. And at the very end, it pops register 4 and the program counter off of it. This is a neat way to cheaply return, because in popping the value from what was the link register at the time the function entered back into the program counter, it can skip restoring that. We also see a BL instruction in the middle, which calls another function within the program. Jumping there, I find a valid function, which tells me that this is correctly loaded. When you have your image and you begin to understand it, you're generally trying to do it for some reason. One reason might be to change the firmware in the physical device. But another useful thing that you might want to do is extract a library from the physical device so that you can run it on your desktop. This is especially true if the library is proprietary, or if you can't purchase a copy. So this radio, the Titera MD380, has a proprietary audio codec called MD+2. And if you want MB+2, there's an open source decoder, but there is nothing open source that will encode the audio. Instead, you're supposed to purchase a dongle that plugs into the serial port. You're supposed to send your audio samples out the serial port and then get back the compressed packets. So what you can do instead, which is I explained in Popper GTFO 13.5, is you can take the firmware image that you now understand because you reverse engineered pieces of it, and you can relink it to be a Linux ARM executable. You can then compile your own C code to run against that library. And the end result is that you have a Unix command line tool that is able to call the proprietary library functions of the physical radio. And because it has the correct code and it has the correct RAM, everything is in the correct position and everything still works. These are the GCC 9 commands to actually perform the linking. The gist of it is that I'm telling it to load the firmware image where the firmware would go at 080C000. So this loads experiment.img as our firmware where the firmware should go. And then what this does is this loads ram.bin into memory where the RAM should go. And I also give it section names so that my linker can provide pointers for this back to my main function. And when I link all of this together, I can then call into these functions. So the first thing that I do is I make a function pointer to the same firmware address as I found a function that does nothing but return. And what this psnippet does is it makes that function pointer, and then it calls it. And if it doesn't crash, that means that it has called into the firmware and successfully returned. If it crashes, it might be because the page is not executable, or it might be because of another mistake along the way. After I have a very short function working, I can then take a much more complicated function. MB decode wave. This is the function that takes a compressed AMBE audio packet as the radio would receive over the air, and it decodes it into a wave buffer that will be played out the sound card of the radio. And this is how you receive digital audio and hear it as voice that you understand. Now, you can see from my comments that I don't really understand what all of the parameters of this function do. I know that A5 and A4 are always 0, so I just make them 0. The buffer is, I think, a temporary buffer, and I use the one that was already loaded into RAM on the device because there might be tables that are required. And then also A7 is always the same address inside of SRAM at 2001, 1224. I just repeat that same address from what I see in the disassembled firmware. I don't actually know what it means or what's located there. And I don't have to, because as far as that function is concerned, everything that it expects in flash memory is at the correct address. And everything that it expects in RAM is at the correct address. So if I call it with the same parameters, it performs the same functions. This audio codec happens to have a copy protection mechanism, which I didn't notice when I first emulated it, because in my emulation, the copy protection check had already passed. So by running the firmware image that I've dumped out of the real radio and the SRAM that I've dumped out of the real radio, it's almost like I've paused the running program inside of the physical hardware and then migrated it into a Unix process. and continue time off from there. Part of the weirdness of this function is that in AMDE you have 2 time slots, so you have to call the decoder twice, and only once it will work. So I just double that up. But the end result is that I have an ARM Linux executable which runs perfectly fine under QEMU. So it doesn't matter that my desktop is an Intel Xeon or whatever, which is then able to call back into the firmware. If I were doing this for a commercial project instead of a hobby project, or if I were more diligent in the quality control for my hobby projects, I could use this to write unit tests and integration tests to know that my understanding of the meaning of the firmware and the locations of the functions were correct. There are some other nifty tricks that you should know. When you're reverse engineering desktop software, we've worked our way to a point in the world where most new software uses UTF-8. And there are some exceptions. Like if you're looking at very old software, you might find national standard, or if you're looking at Windows software, you might find Unicode 16 instead of UTF-8. In firmware for ARM, it's surprising, but you'll very often find the Chinese standard called GB2312. So sometimes when you're looking through a firmware image for a device that has a screen display in Chinese, but not in English, and you run strings on it, and you look for Unicode strings, and you find none of it, you will still find GB2312 strings if you try that. And you can then run them through Google Translate and use those strings to understand the meaning of the code involved. I have a GitHub project that dumps these strings because the standard tools don't seem to like that format. Magic constants are also useful. In the case of reverse engineering the radio firmware, there was support in the protocol for like an emergency shouting mode where every radio that hears the message will decode it. You use this if you need to address everybody on the network, even though some of them might not be configured to receive you. By searching for the address that you send that audio to, I was able to find the functions that control whether the radio plays incoming audio or not, which allowed me to make promiscuous mode to decode all incoming audio. You can also search for masks. In this particular protocol, addresses are 3 bytes long instead of 4 or 8 or 16 or whatever else you would want. So by searching for 00FF, I could find all of the masking operations that were trying to drop off the extra byte that was not a part of the address. And that allowed me to locate large parts of the networking stack. You can also hunt for reference code. So in my case, I was attempting to reverse engineer a device which locked its own firmware. And I needed to find the function that locked the firmware in order to disable it. To do that, I looked at the manufacturer's reference design, and they provided this example function, which was used exactly with no modification by the radio vendor. It was statically linked into the firmware image. So I could look at what assembly code was generated by compiling this, and then I could search for everything similar. And by searching, I was able to find the correct function in very little time. You can also automate a lot of the drudge work of sorting through the image and identifying things. So one very useful thing to do is to realize that most functions are targets of a branch and link instruction. And the only exceptions to that in a normal application will be functions that are called by pointer, where you will find a copy of the function pointer either in Flash or SRAM, and interrupt handlers, which are in the interrupt handler table. So if you run through memory and you find every branch and link instruction and then look at its target, and then you instruct your disassembly tool through an IDA-Python script or the scripting for whatever other tool you're using, you can automatically identify all of those functions, and then begin working with the entry points all known, or even instruct IDA to decompile the entire image and then search through it as C code without having to look at the assembly. And when the vendor releases a firmware update, and you would like to stay up to date with that firmware, but you've written your patches against an older firmware image, you need some way to automatically port. Because if you do all of this by hand, then you forget why you did certain things or why you patched out certain functions, and it becomes difficult to maintain. Instead, it would be nice if all of your patching were performed in C in the style of replacing a function of a particular name, and the names you could apply to one version of the firmware and automatically move to future versions. So if you're trying to do this between, let's say, Adobe PDF Reader on Spark and modern Mac OS, that becomes a hard problem because you have different compilers, different instruction sets, different major versions, and there are very smart people who work on those problems and get results on them. In my case, I'm interested in getting an answer immediately with a couple pages of C code. So the way that I do this is that I realize that embedded developers usually use the same version of a compiler. They don't update their compiler frequently like a desktop Linux user might. And when you're using the same compiler to compile different versions of the same firmware, most of the functions don't change at all. And those that do change, are usually for the small feature that gets fixed. They're not necessarily the same function that you might want to hook. So you're usually looking at the exact same assembly code linked to a new address. And when it's linked to a new address, the targets of the BL instructions, which means branch and link, which is the thumb version of a function call, those change, but nothing else changes. So we can do this trick where you can compare how similar two functions are by stepping through every 16-bit word in the function, with A being the word in the first function and B being the word in the second function. And if A equals B, then great, they're identical and you can move on. If they don't equal each other, but they both have a most significant nibble of F, meaning both of them have their most significant 4-bit set, then that 16-bit word is part of a branch and link instruction, and it doesn't matter that it changed because it's expected to during relocation. So this lets you come up with a very, very short C function that will race through large firmware images and directly compare their functions in order to identify which ones are equivalent so that you can port your symbol names. If you'd like an example of this, there's code in the symbols directory of the MD380 tools project. We've gone over a lot in this lecture. I hope that you picked up some nifty tricks that you'll use in your own projects. I do not expect you to remember every detail, and I certainly wouldn't if I watched it myself. But it's the nifty tricks that save you when you're blocked or that allow you to hack something that you might otherwise get stuck on that are the valuable things that I look for in these lectures.
If anyone wants to have reference material for this, POCR GTFO 11, 11.6 has the full article that some of this content came from. So you can also look at that if you want reference.
Howdy, Adrian.
Hey, so I'm sent out a query for questions. One question we got was what modern devices have the Cortex M in it? And I was just doing some noodling while you all were talking, and I found that iFixit is a pretty good place to find what chips are in what things, since they do teardowns and they verbally, they write out what chips they find and identify the chips.
Oh yeah, their teardowns are great. They also show you like which tiny ribbon cable you're most likely to screw up when you open the device.
Yep, this thing will tear if you pull that screen off. Yep. Yeah, so I found out like some of those hoverboards use them. The Apple TV uses them. iPod Touch 6th generation. The Pebble watches, smartwatches, use them.
So in the Apple TV, this won't be the main CPU. This will be off on the side.
So it's in the they use it both in the main unit and inside the remote.
Okay,
Yeah,
maybe the controller. Does it have a chip name?
It's for the RF4CE, Travis, in that one, I believe.
Okay.
Yeah, so a lot of these, that's a great point, Adrian, right? A lot of these will be in, you'll often find these families in smart remotes. So I don't know specifically if it's the M3 and M, but think of any remote that you're pushing your yeah, I'm pretty sure they're actually M3 based, that you push and do voice to tell your TV what you want to do, for example, whether that's a TV, an Apple product, or a third party. Typically, these are integrated into some of those radio chipsets or based on this architecture.
And if you have
if
you have like a small consumer device with an LCD screen, but that clearly isn't as powerful as Android, it's quite likely one of the higher end Cortex M chips.
Cool. Yeah, it's what it looks like with a few devices here. The Oculus Rift, multiple versions of the Oculus Rift also use it, and the 2nd generation Nest. So yeah, that was pretty cool. I was trying to think like how would I even find that, because manufacturers usually don't publicize that, what chips they're using for what things, and I realized iFixit, that's what they specialize in.
So the manufacturer won't publicize it, but very often you can find out which chips they use from their FCC filing.
Yeah, we see a lot of leaks come from that before devices come out sometimes. Well, very cool. Yeah, so I'm not seeing any questions. So thank you both very much for the talk. And there's definitely some discussion going on the Discord, which has been fun to have.